You think you're unique. Everyone does. Your face, your fingerprints, your memories, the whole story of you feels irreplaceable. And in one sense it is. But that's not actually the interesting part. The interesting part is why. Not in some poetic philosophical way, physically, mathematically, at the level where the universe actually runs. Because here's what nobody tells you when they say you're one of a kind. You're made of particles. Electrons, quarks, photons, pieces so small they don't even have a surface. And every single electron in your body, every one, is completely, perfectly, fundamentally identical to every electron in a rock on Mars, in a star in a galaxy you'll never see, in the fingernail of someone who died 1,000 years ago. Not similar, identical, interchangeable, zero difference, none. So if the building blocks are utterly indistinguishable, if the universe is assembled from pieces that are all exactly the same, then what precisely makes you unrepeatable? That question sounds like philosophy. It's actually physics, and the man who gave us the tools to answer it was Pauli Dirac. Let's slow down on what identical actually means here, because your intuition is going to fight you on this. Take two red cars off the same production line. Same model, same color, same year. They look identical. But they're not really. Different atoms, different microscopic scratches, different histories. If you looked close enough, you'd always find a difference. Now take two electrons. You cannot do that. There is no looking close enough. There is no hidden scratch, no serial number stamped somewhere we haven't looked yet. They don't have individual identities in any physical sense. This isn't a limitation of our instruments, it's a fact about reality. Quantum mechanics doesn't just say we can't tell them apart, it says there's nothing there to tell apart. This sounds like a subtle distinction. It isn't. It breaks things. In classical physics, the physics of Newton, of everyday objects, if you have two particles and two boxes, you can put particle A in box 1 and particle B in box 2. That's one arrangement. Swap them and you get a different arrangement. Two possibilities. So you count 2. But if A and B are truly identical, swapping them doesn't give you a new arrangement. It gives you the same one. There's only one possibility, not two. You count 1. Change how you count, and you change every statistical prediction physics makes about matter, temperature, pressure, the behavior of electrons in metals, everything. Dirac saw this, and he worked out the mathematics, together with Enrico Fermi, of what happens when you take quantum indistinguishability seriously. The result is Fermi-Dirac statistics, and what falls out of it is one of the most important facts in the universe. There's a rule. It comes directly from this statistics, from the mathematics of identical particles, and it sounds almost too simple to matter. No two identical fermions can occupy the same quantum state at the same time. That's the Pauli Exclusion Principle. And I want you to feel what it's actually saying, not just file it away as a fact. The universe doesn't forbid two electrons from being in the same state, the way a bouncer refuses entry. It's more fundamental than that. If two particles are truly identical and in the same quantum state, there's a sense in which there isn't two of anything. The mathematics just doesn't allow a second one to exist there. Reality refuses to make a copy. Think about what that means for an atom. You've got a nucleus, and electrons want to crowd around it. Without exclusion, they'd all pile into the lowest energy state. Every atom would collapse into a tiny, featureless blob. No structure, no shells, no chemistry, no molecules. No proteins, no DNA, no neurons firing in your brain right now as you follow this thought. The fact that matter has shape, that atoms are structured, that elements behave differently from each other, that a carbon atom does different things than an oxygen atom, all of that comes from the Pauli Exclusion Principle. All of it comes from the fact that identical particles can't stack on top of each other in quantum state space. The universe has structure because it enforces uniqueness at the smallest level. So now we can actually answer the question, why are you unique? Your electrons are not unique, your quarks are not unique. Every particle in your body has an exact twin, billions of exact twins, scattered across the cosmos. The stuff you're made of is completely ordinary, completely interchangeable, completely unremarkable. But you're not just stuff, you're an arrangement. Every particle in your body has a quantum state, an energy level, a spin orientation, a position, a momentum. The combination of all those states for all those particles in all those relationships, that specific configuration is what you are. Not the ingredients, the pattern. And here's where the numbers become almost incomprehensible. Your body contains something like 7 octillion atoms. That's a 7 followed by 27 zeros. The number of ways you could arrange the quantum states of all those particles, all those interactions, all that structure, it isn't just large, it's so astronomically large that the observable universe, running for its entire 13.8 billion year history, has almost certainly never produced this configuration before. And given the way entropy works, the way time runs, the way the universe expands and cools, it almost certainly never will again. You are not unique because you're made of special material. You're unique because the pattern has never been repeated, will never be repeated, can't be repeated in any practical sense. And Dirac's framework, the statistics, the exclusion principle, the mathematics of identical particles, is exactly what lets you define that pattern precisely. Without it, arrangement is just a word. With it, it's a calculable, physical, real thing. Here's where I have to be honest with you, the way Feynman always insisted on being honest. We've explained that your pattern is unique. We haven't explained why the particles that make up that pattern are identical in the first place. Why does every electron in the universe have exactly the same mass, the same charge, the same spin? Not approximately, exactly, to every decimal place we've ever measured. An electron here and an electron in a galaxy 10 billion light years away, which has never interacted with anything near us, identical. Same number, every time. We don't know why. There's a beautiful idea, technically wild, and Dirac didn't dismiss it, proposed by the physicist John Wheeler. Maybe there's only one electron zigzagging back and forth through time, appearing at every point in the universe simultaneously, weaving through the entire history of the cosmos in a single impossible trajectory. That's why they're all identical. They literally are the same particle. It has problems, real ones. The numbers don't quite work out, but the fact that someone could seriously propose it and that serious physicists entertained it tells you something about how strange the underlying question really is. When we say all electrons are identical, we're giving the observation a name. We're not explaining it. Quantum field theory gets closer. It says electrons are excitations of a single electron field that permeates all of spacetime, and of course all excitations of the same field have the same properties. But then you have to ask, why does this field have the properties it has? Why these numbers and not different ones? That question currently has no answer. We describe, we don't fully understand. And I think it's worth sitting with that for a moment, rather than rushing past it. Pull back now, way back. The same laws that make every electron identical, those laws are also what give matter structure. The exclusion principle doesn't just prevent copies, it builds complexity. It forces electrons into shells, shells into chemistry, chemistry into biology, biology into the nervous system sitting behind your eyes, reading these words. You exist because the universe enforces a kind of radical sameness at the bottom. And that sameness, that refusal to allow copies of the quantum level, creates all the difference of the level you actually live. Without identical particles, there's no exclusion. Without exclusion, there's no atomic structure. Without atomic structure, there's no chemistry. Without chemistry, nothing. No stars burning stably, no planets forming, no molecules complex enough to store information, to replicate, to evolve. No you. You're not unique, despite the universe being made of interchangeable parts. You're unique because it is. The sameness at the bottom is what makes the difference at the top possible. Dirac didn't set out to explain why you're one of a kind. He was trying to write down an equation that was consistent with both quantum mechanics and special relativity. But the mathematics pulled him somewhere real. It always does when the mathematics is right. And Dirac trusted that more than almost anyone who ever lived. He believed that beautiful equations were pointing at something true, even before the experiments confirmed it. And here he was right. So here's where we land, and I don't want to wrap this up too neatly, because it isn't neat. You are a configuration, a specific astronomically improbable arrangement of identical parts, held in shape by rules that emerge from the deepest structure of quantum mechanics. You won't be repeated, not because the universe has been careful with you, not because you were designed, but because the space of possible configurations is so vast, and time is so finite, and entropy moves in only one direction, forward, always away from what was. The building blocks of you have existed since minutes after the Big Bang. Your hydrogen atoms are almost as old as the universe. And in all that time, in all those rearrangements, all those stars and supernovae and chemical reactions, this particular configuration has existed exactly once. That's not a comforting thought dressed up as science. It's what the math actually says. The mystery doesn't get smaller when you understand it. It gets stranger. The deeper you push into why you're unique, the more you find that the universe's deepest commitment to sameness is what makes your uniqueness physically real. And maybe the most Dirac thing about all of this, the most honest thing, is that we still don't know why the particles are identical. We don't know why the universe chose these numbers, these fields, this particular version of the laws. We know what the rules do. We don't know where the rules come from. That question is still open. It might always be open. But ask it anyway. Ask it the way Dirac asked questions, quietly, precisely, without needing the answer to be comfortable. Because the asking is what physics actually is.